Hello. This podcast is on rotational dynamics and energy. Specifically, we're going to learn about Newton's second law of rotational motion. We're going to learn how rigid body diagrams can help us identify net torques. We'll look at objects that move both translationally and rotationally at the same time. We'll see the role that energy, work, and power play in rotational motion. And finally, we'll see how we can use conservation of mechanical energy to analyze rotational motion. First, let's review some key rotational quantities and relationships. So we learned about angular position, angular displacement, angular velocity, angular acceleration, and their relationships to our translational quantities: displacement, velocity, tangential acceleration, mass, and force. And we had, for constant acceleration, we had our three translational equations, and for constant angular acceleration, we have similar equations for describing rotational motion. Let's take a look at Newton's second law of rotation. The angular acceleration of an object is proportional to the net torque and inversely proportional to the rotational inertia. Notice this is very similar to Newton's second law of translational motion. And let's go ahead and prove this rotational motion law, starting with the translational motion law that we already learned. But first, let's bring up these translational rotational relationships. And we'll start with our original Newton's second law. And we'll go ahead and substitute these expressions for force, mass, and acceleration. Then we'll rearrange to find torque. And we know that if the force is perpendicular to the lever, we can simplify this expression to Newton's second law of rotational motion, which is the net torque is equal to the rotational inertia times the angular acceleration. Let's move on and take a look at a problem. A force of 10 newtons is applied to the outer edge of a resting ball in the positive tangential direction. If the ball has a radius of 0.25 meters and a moment of inertia of 0.50 kilograms meters squared, what is the angular velocity after 5 seconds? In this situation, the force is constant and the lever it's applied to is constant, so we know that there's a constant torque. And because there's a constant torque, we know that the angular acceleration will be constant, so we can use our kinematic equations for a constant angular rotation. But first, we need to find the torque, then we can find the acceleration. So we go ahead and use our torque equation, plug in our values, and we find out that there's a torque of 2.5 newton meters applied to the ball. We can use Newton's second law to find the angular acceleration. We rearrange the second law and find the acceleration is 5 radians per second squared. Now we can go ahead and use one of our kinematic equations, and we're going to go ahead and use the first equation, and the angular velocity winds up being 25 radians per second after 5 seconds. Let's move on and look at rigid body diagrams and net torque. So rigid body diagrams are analogous to free body diagrams in translational motion. They identify the axis of rotation, the force, and the lever. So in this case over here, we have a physical situation with a rod pivoting or rotating about a hinge. So we go ahead and use this triangle to represent the pivot point or axis of rotation, and that is at the hinge. Then we go ahead and put forces where they act on the object. And the force of gravity or weight of an object can be shown acting at the object's center of mass. We also want to identify the lever length. So if the total rod was L, then the length of this lever that the force is applied to is 1/2 L. This acts as a guide to calculating net torque. Next, when we're analyzing rotational problems, we need to realize that the governing equation is Newton's second law of rotational motion. That is what's going to predict the rotation. Let's use this to solve a problem. A uniform rod of length m and mass m is free to rotate about a frictionless pivot at one end in a vertical plane. The rod is released from rest in the horizontal position. What is the initial angular acceleration of the rod? So that is this physical situation here. We already have our free body diagram. So let's go ahead and solve this problem. We use Newton's second law of rotational motion. We rearrange to find angular acceleration, and then we plug in some expressions for torque and rotational inertia. This expression comes for a rod rotating about its end. We substitute these into Newton's second law, and we wind up with a general expression, in this case for angular acceleration, 3g divided by 2l. And of course, if we knew the specific length, we could go ahead and calculate this angular acceleration. Notice that the mass is not involved in the final determination of the angular acceleration. And then once we have the angular acceleration, we can go ahead and use our rotational kinematic equations to predict position, displacement, and angular velocity. So this is the general approach to solving these problems. Let's take a look at another problem. Here we have a one-piece cylinder shaped with a core section protruding from the larger drum. So here we have the larger drum. Here we have the smaller section protruding out of the screen towards us. The cylinder is free to rotate about the central axis as shown in the drawing. A rope wrapped around the drum of radius R1 exerts a force to the right on the cylinder. A rope wrapped around the core of radius R2 exerts a force F2 downward on the cylinder. What is the angular acceleration of the cylinder if we have these values for the radii, forces, and masses? Our first step is to draw a rigid body diagram, and the sketch here has just about everything we need in that diagram except the axis of rotation, so we go ahead and draw that and locate that. Next, we need to find the equation for rotational inertia of a solid cylinder about its symmetry axis. Then we need to use and rearrange Newton's second law. We need to substitute our expression for torque and our expression for rotational inertia. Notice here that the solid cylinder has two different diameters, so we're going to add the rotational inertia for the larger diameter, and we're going to add to it the rotational inertia for the smaller core. We go ahead and plug in our numbers, and we find out that its angular acceleration is 1 radian per second. It is causing counterclockwise rotation. From here, we can use the rotational kinematic equations to predict the different rotational quantities. Moving on, let's look at some instances where objects move rotationally and translationally at the same time. For example, we can have a ball or tire rolling downhill. In this case, the tire rotates about its symmetry axis and the center of mass accelerates down the hill. We can have a yo-yo, and here the yo-yo rotates about its symmetry axis and the center of mass accelerates downward. We also have systems like Atwood machines, atoms and molecules, and yes, the moons, planets, stars, and galaxies. And here, if we look at Earth, Earth rotates about its north-south pole, and the center of mass accelerates in elliptical orbit around the sun. So let's look at the governing equations when we have simultaneous rotational and translational motion. Both Newton's second laws have to hold true, and this relationship ties the two together. Let's take a look at a problem using a yo-yo. So it's at rest and it's allowed to unwind under the force of gravity, and it has a mass of 1/10 of a kilogram, a radius of 5 centimeters, and a moment of inertia for a solid disk rotating about its symmetry axis. First, we want to draw the rigid free body diagram, and so over here we are showing the axis of rotation, we're showing the levers. Of course, the weight is acting at the center of mass, which is also the axis of rotation. So this weight has no lever, but the tension of this string does have a lever, and it's equal to the radius of the yo-yo. Next, we want to write the three governing equations in terms of our specific values we have. And so we go ahead and come up with these three equations. So we have three unknowns: tension, acceleration, and angular acceleration. So we have three independent equations. We need to solve this system of equations. Notice our final expression for angular acceleration is 2g divided by 3r. We go ahead and plug in our numbers, and we find out that the angular acceleration is 130.7 radians per second squared. Notice that mass does not affect angular acceleration. Then we want to solve for acceleration, and we find out that the general expression is 2/3 g. We plug in our numbers and find out that the acceleration is 6.5 meters per second squared. Notice mass and radius don't affect acceleration. These are two important conceptual points. Finally, before leaving this problem, I want you to recognize that once we have this system of three equations, we can solve for any of these three unknowns. This problem didn't ask us to solve for the tension force, but once we have these three equations, we could solve this system and find the tension force. Let's move on. And let's look at an Atwood machine. So we have two masses, M1 and M2. They're connected by a light cord. That means we're not going to have to account for the mass of the cord. And they pass over a pulley with mass M and radius R. This is different. In previous Atwood machine problems, we've had a massless pulley. And we'll see why it's a big difference when the pulley actually has mass. And the pulley has a rotational inertia of I. We want to assume there's no slippage between the cord and the pulley as it passes over the pulley. And what is the acceleration of these two masses, 1 and 2? So we want to draw a rigid body diagram for the pulley and free body diagrams for the masses. So we go ahead and do that. Next, we want to take a look at the three governing equations, and we want to rewrite them in terms of our specific quantities. Notice that T2, the tension on the right-hand side of the pulley, has to be greater than the tension on the left-hand side. Otherwise, the pulley wouldn't rotate clockwise. So even though it's the same cord, when it goes over this pulley with mass, the tension force on the right-hand side is stronger than the tension force on the left side. This is important conceptually because when the pulley is massless, these two tensions on either side of the pulley are the same. But when the pulley has mass and it has rotational inertia, when it's rotating clockwise, tension force on the right-hand side of the pulley is going to be greater than the tension force on the left-hand side. Then we go ahead and write our net force equation, and we do it for both tension forces. Of course, the acceleration is the same for both masses, so we don't have to distinguish between acceleration 1 and acceleration 2. And we write our fourth governing equation. We're running out of room, so let's move on to a fresh screen, bringing over these four equations. So we have four unknowns, T1, T2, acceleration and angular acceleration, and we have four equations. So we need to solve this system of equations. This leaves us with an expression for acceleration. Notice the denominator reflects that the energy used to rotate the pulley reduces the mass's acceleration. If you remember when we were studying translational motion, the formula for an Atwood machine would be the same as this, except this term I over R squared would not be there. So this adds to the denominator, which reduces the acceleration. And conceptually, this is important. It takes energy to rotate an object, and that takes energy away from its translational motion. So when something is rotating and moving translationally at the same time, it will move more slowly than when it's just moving translationally without rotating. And final note, once we have this system of four equations, we can solve for any of these unknowns. In this problem, we were asked to find acceleration, but we could have found T1, T2, or angular acceleration. Let's move on and look at rolling. First, conceptually, rolling is the simultaneous rotational and translational motion of an object, and that object needs a net torque and a net force to start rolling. Let's look at an example. Here we have a force that's applied to the object away from the axis of rotation, so that creates a lever, which creates a torque and causes rotation. Friction often supplies the force that creates the torque. If there's no slippage, we know that the translational velocity is equal to the radius times the angular velocity. And if there is slippage, then this expression doesn't hold true. But let's take a look at this physically. Friction occurs at the interface of the two surfaces, and notice that it provides a torque because it's a force applied to a lever. So even if the other force is at the axis of rotation and contributes no torque, the friction is providing the torque for the rotation. And finally, if there is no net torque, the object will slide instead of roll. And here we have a case where a force is occurring at the axis of rotation. There's no lever. If there's no friction between the two surfaces, there is no other force, and we're going to see this ball slide across the surface instead of roll. Let's look at a specific case where objects are rolling downhill. First, let's look at some things conceptually. For a symmetrical shape with uniform density, shown here, gravity acts at the axis of rotation, so it creates no torque. Friction applied to the lever creates the torque. And the net force is the x component of gravity minus the friction force. For asymmetrical shape or non-uniform density, as shown here, gravity creates torque if the center of mass does not lie on axis of rotation. So notice here, the center of mass of this object is over here away from the axis of rotation, and that creates a lever. So this gravity force will cause rotation. Friction is still there and it adds to the rotation, but it's not necessary. So even if this was a frictionless plane, this object would roll downhill. And the net force in this case is also the same as before, the x component of gravity minus the friction force, because again, we're looking at forces that are parallel to the inclined hill. Let's take a look at this quantitatively. An object with mass m, radius r, and moment inertia I, and coefficient of friction mu rolls downhill. Assume there's no slippage. Find the expression for acceleration in these terms. So here's a physical sketch of the situation. Our first step, we want to draw a rigid free body diagram. Well, this has everything in it except the axis of rotation, so we'll go ahead and add that to complete our rigid body diagram. Now we want to write our three governing equations in terms of our specific values we have for this problem. And we go ahead and write those. That gives us three unknowns: the friction force, acceleration, and angular acceleration. And so we can solve this system of equations. And we find that the acceleration is equal to this expression. And the denominator reflects the fact that rotation takes energy. This term deals with the rotation of the object, and notice that it will reduce the translational acceleration. Let's continue to do a little more work with this general equation. And so we know for all objects their rotational inertia is in the form of k mr squared, where k is a constant based on the shape and mass distribution of the object. So let's go ahead and substitute this expression into the acceleration equation, and we go ahead and do some rearranging and simplifying, and we find out that the acceleration is equal to this. Notice the mass and radius do not affect rolling downhill. The only thing that affects rolling downhill is this constant k, and that's based on the shape and mass distribution. So what's important to know conceptually is that when objects are rolling downhill, their acceleration is going to be obviously a function of the gravitational field strength and the slope of the hill, but also how the mass is distributed about the shape of the object. Now that you know a little bit about rolling downhill, let's see if you can predict the winner of our downhill rolling derby. Our contestants are the thin spherical shell, solid cylinder, hoop, and solid sphere. Pause the video now and make your prediction. Conceptually, the object with its mass distributed the closest to the axis of rotation will win. Mathematically, the object with the smallest k value will win. So here's our placements. First place, the solid sphere. Second place, the solid cylinder. Third place, the hollow sphere. And last place, the hoop. Go ahead and see if you can answer this question. Which rolls downhill faster, a tire or a tire mounted on a wheel? Pause the video and make your prediction. Well, the winner is the tire and the wheel because it replicates a solid cylinder, whereas the tire alone represents a hoop. Let's switch gears and talk about energy in rotational motion. First, let's review some energy concepts. We know all changes in motion require energy transfer, and all objects store energy in their motions. So let's take a look at the kinetic storage mechanism. For translational motion, we have this relationship. For rotational motion, the kinetic energy of rotational motion is 1/2 rotational inertia times omega squared. Notice conceptually that is the same as what we had for translational motion. 1/2 times inertia times velocity squared. The total kinetic energy is thus the sum of these two kinetic energies. Mechanical energy is made up of the translational kinetic energy, the rotational kinetic energy, and of course the gravitational potential and elastic potential energy. We can rewrite that in terms of some more basic quantities. Let's take a look at how we derive this expression for rotational kinetic energy. And so what we first need to realize is that a rigid body is made up of an infinite number of these small masses, and its total rotational kinetic energy is made up of all of these small particles' translational kinetic energy. So here is the derivation. Let's take a look at a simple energy problem. So we have a solid ball with a mass of 10 kilograms and a radius of 1/2 meter with a moment of inertia of 1 kilogram per meter second, and it's going down an incline at a rate of 3 radians per second. What's its rotational kinetic energy? Well, we're just going to go ahead and use this expression up here and plug in our values, and we find out that it has 11.3 joules of rotational kinetic energy. Moving on, let's look at work and power in rotational motion. First of all, we know work is a transfer mechanism that transfers energy into or out of a rotating system or rigid body. And let's take a closer look at that mechanism. For translational motion, work is equal to an object displaced parallel to a force, and for rotational motion, the work is equal to the torque multiplied by the angular displacement. And the total work is just the sum of those two quantities. Power is the rate at which work is performed, and that's just dW dt, and we can rewrite dW as ds dt, and that simplifies to force times velocity. For rotational motion, it's dW dt, and we can rewrite the dW as d theta dt, which tells us that the rotational power is equal to the torque times the angular velocity. And the total power of the motion is just the sum of the translational power and the rotational power. Now, let's go ahead and take a look at the derivation for this expression for rotational work. And the rotational work is based on a single force applied at a point somewhere away from the axis of rotation. And we're left with the expression for rotational work. Now, let's take a look at the derivation for the rotational power. We start with dW dt, and we use this expression and substitute it for dW, simplify it, and we're left with this expression for rotational power. Let's take a look at the work energy theorem in rotational motion. We know work performed by external forces equals the change in kinetic energy. And translationally, we express it as the work into or out of a system is equal to the change in the translational kinetic energy. Well, no surprise for rotational motion, the rotational work is equal to the change in the rotational kinetic energy. And for the total motion, the total work is equal to the sum of the change in these two kinetic energies. So let's look at the derivation for our rotational work energy theorem, and it starts with Newton's second law of rotational motion. And we're left with this expression. Let's take a look at our rolling ball from a few moments ago and apply some of our new energy equations to its analysis. So again, it's a solid ball initially at rest with a mass of 10 kilograms, a radius of 1/2 meter, and a moment of inertia of 1 kilogram meter squared. It's rolling down an incline with an angular velocity of 3 radians per second, and now we're told that at 5 seconds, its translational velocity is 6.2 meters per second. How much work was performed on the ball? For this, we know to use the work energy theorem, so we need to take into account the translational kinetic energy and the rotational kinetic energy, and we know that the change in those two is going to be equal to the work that was put into the system. So we go ahead and plug in our numbers, and we find out that it was 199.8 joules. And as a follow-up question, what is the power input to the ball? Well, for that, we want to use our power equation. Now, we cannot use this form of it because we don't have the force and the torque, but we can use this form, the change in work divided by the change in time. So we had 199.8 joules put into the system over 5 seconds, and that comes out to 40 watts. Let's move on and see how we can use the conservation of energy to analyze rotational motion and simultaneous translational rotational motion. First, let's put our energy equations up here because we'll be needing them. And here we have a basketball initially at rest, and it rolls down a 5-meter high slope. Okay, so that's quite a slope. Notice it's not linear, so the force is constantly changing. This would be a tough one to solve using Newton's second laws and the kinematic equations, but it's much easier using conservation of mechanical energy. So we want to find out the velocity at the bottom of the ramp. Here are the quantities. This is the actual radius of a basketball and mass of a basketball, and we're going to treat the basketball as a thin spherical shell, and that gives us this expression for rotational inertia. If there's no slippage between the basketball and the ramp, in other words, if the ball rolls down the ramp without any sliding or slipping along the ramp, then energy is conserved. So that's important to know because now we can use the energy conservation equation. And so that simply tells us that the final energy is equal to the initial energy. We know that at the bottom of the ramp it has no gravitational potential energy, but it has kinetic energy. And at the top, it has no kinetic energy, but it has gravitational potential energy. And then we can go ahead and write that in more basic quantities. So keeping in mind that the ball is both rolling and moving translationally at the bottom of the ramp, so we have to account for both kinetic energies. And the initial gravitational potential is just mgh. We know the rotational inertia, and when there's no slipping, we know that the velocity is equal to r omega, so we can rearrange that and come up with omega. And now we can plug those terms into the equation, and we can solve for velocity, and we're left with, in general terms, it's equal to the square root of 6/5 times gh. And plugging in our numbers, we get 7.7 meters per second. Notice that without rolling, without that rotational motion, the expression for the velocity would have been the square root of 2gh, and the velocity would have been 9.9 meters per second. So once again, we're seeing that when an object rolls, it is giving up some translational acceleration in order to provide energy for the rotational motion. Now let's talk about friction and slipping. I had mentioned that in the previous problem, and we said that it was important that the basketball did not slip as it rolled down the ramp. And let's take a closer look at that conceptually. Typically, we think of friction as a non-conservative force, and that occurs when two surfaces in contact with each other slide or slip past each other. This dissipates energy out of the system. And in this case, the translational velocity is not equal to the radius times the rotational velocity. Let's look at the situation where friction does act as a conservative force. And this is when we have two surfaces in contact with each other and they move across each other without slipping or sliding. So examples would be a basketball rolling or anything rolling against a surface that isn't slipping. That friction force creates the torque for rotational motion, and that performs work that transfers the energy from the translational kinetic energy to the rotational kinetic energy, or vice versa. So here, this force is creating a torque that performs work and transfers the energy from one useful mechanism to another useful mechanism. Up here, when friction's a non-conservative force, it's not doing any useful work and it's transferring the energy into the dissipated mechanism. Down here, it's performing work. And in this case, we know that the translational velocity is equal to the radius times the angular velocity. So let's look at some examples. Your car tires rotate on a dry road without slipping. Well, friction transfers rotational motion to translational motion. That's what causes your car to move forwards. Even though the motion that the engine's causing is rotational motion, that friction force causes your car to move translationally without dissipated energy. Let's switch to this situation. Car tires slip as you're going up an icy hill. So the tires, you know what happens, the tires rotate faster and faster, but the car slows down. What's happening is friction transfers some energy to translational motion, but much of the energy is being dissipated. Well, this wraps up our lesson. Let's summarize what we've learned about rotational dynamics and energy. Objects that rotate obey Newton's second law of rotational motion. Objects with simultaneous translational rotational motion obey both versions of Newton's second law. Rigid body diagrams visually describe the physical situation for rotation. They're analogous to our free body diagrams in translational motion. And here are the motion equations that govern rotational and translational motion. We learned that the role of energy in rotational motion is similar to its role in translational motion. Rotational motion requires energy, therefore objects with simultaneous translational rotational motion do not move as fast as those that don't rotate. These are the energy equations that we learned that govern motion both rotationally and translationally. Lastly, we learned that friction is a conservative force if there is no slipping or sliding. Well, this ends our lesson. I hope you found it helpful and have a good day.